The next presentation this morning is going to be given by Michele Mosca, a colleague in CNO as well. Mike is a Waterloo alum. He did his B-Math in 1995 in CNO and in Pure Math, and his doctorate in Oxford in 1999 on quantum computer algorithms. So he joined Waterloo as a faculty right after, and is currently a full professor in CNO. So Mike has many accomplishments, and that's why I have this cheat sheet here. And as you can also tell from the logos on this first slide, he has done quite a bit. So he is the co-founder of the world-renowned Institute for Quantum Computing. He's also a founding member of the Perimeter Institute. Mike is the co-founder of his own company, Evolution Q. He is one of Canada's top 40 under 40 in 2010. He received the Queen Elizabeth II Diamond Jubilee Medal in 2013. And just recently, last year, he received the knighthood in the Order of Merit of the Italian Republic. And with that, I would like to welcome Mike.
So just to start things off on a positive note, one of the big challenges for society is that security is, since the beginning of time, basically an afterthought. We wait for a problem to be very real, and then we have motivation to fix it. And that's more or less served us well, though it's becoming an increasing problem as we develop tools and systems that are instantaneous, scalable, and essentially free. We really do need to rethink how we can be a little more proactive in dealing with security in this cyber era. Okay. So, well, we definitely like to reap the immediate rewards of putting things online and engaging in this digital ecosystem, which is wonderful. It adds a lot of value. It does open up a whole new threat landscape that we've never seen before. And we haven't really started experiencing the true risks or the true dangers yet. And at the basis of protecting not just our information but also our we're talking about Internet of Things now and systems. So protecting our safety as well in this digital era is cryptography. And it's one of the pieces we take for granted because it actually, for the most part, has worked. It's not how people hack into our systems, mostly. It's not. There's few examples that we know of where people actually broke the crypto to get in. They break other pieces of the system, some sort of implementation flaw, physical security, a person makes a mistake. Right? But without crypto, you can't get secure anything using untrusted media. The magic of crypto is it allows you to use an untrusted infrastructure like the internet, and still get reliable, trustworthy results. How can you possibly send something through the internet and know that it was kept confidential and wasn't tampered with and gets to the person it's supposed to get to and came from the person you think it came from? You can't, without crypto, you have to trust every single piece of that system, and it'd be astronomically more expensive and impractical. So it's a wonderful new tool. That's not that new. Actually, crypto's been around, of course, for centuries. But modern cryptography has vastly broadened what we can do with mathematical methods. Okay? Good crypto means you can trust less. You still have to trust something, but you can get away with a lot. You can get a lot more out of a less trustworthy system. Cryptography, in some sense, needs to be the strongest link because it's really the only one that where you can send a message through the internet. Somebody could record it, so someone who isn't able to break it now can record that message and break it later. Right? The other weakness is you can't really time travel back and compromise a person. So it really does need to, it's an essential, the point I want to get across, it's an essential piece, right, of communication and any sort of information processing in the modern era. Now, I said, it's rarely, in the modern era, we haven't really seen cryptanalysis be a problem. But of course, there are examples that we just heard of, right, from Dan earlier. Very famous example in the Second World War. And there was also, we heard a bit, and Ron Mullen told us about some work in the early 80s. And again, these are students and the students of the students of Bill Tutt, not knowing, they were doing cryptography at the time. As Ron mentioned, they were working on this other math problem with a different application. But when they came up with a better way to solve this other problem, they realized it could be used to break codes. These new codes that people were starting to take seriously, implemented in software, they were starting to implement it in hardware, right? Something that was supposed to take over 100 years to break, they broke in a month, and I think probably got it down to minutes with some optimization, right? So imagine that these things had been deployed and we were depending on them, right, for safety and security, and then they were broken. That would be very, very bad, but that didn't happen. So they broke it before we were dependent on these tools. Right, and this got these famous combinatorialists and coding theorists. They caught the crypto bug and started working cryptography and created a great cryptography legacy for Waterloo, for Canada, and the world. Very high impact. I mean, the tools we all use today on our smartphones were developed by Ron, Scott, and others and turned into commercially deployed cryptography. So they didn't stop at writing papers about it. They actually saw the opportunity, the positive practical applications, and made them become a reality. And by the late 90s, they decided, and this is just as they were learning about what Bill Tutt had done in the Second World War, the Center for Applied Cryptographic Research was founded, again, building on the shoulders of giants. And this center actually, so I was in England at the time that this center was started. I'd already finished my undergraduate, but Alfred Menezes came and visited me a couple times and was encouraging me to come back and help start and grow this new center. It already started by the time I came back, but as Scott Vanstone used to put it, they wanted to keep an eye on me. So they wanted me nearby. So I did, and grew the quantum computing effort into the IQC, and the CACR is now essentially grew into and folded into this new Cybersecurity and Privacy Institute, which are two great, gems of the university, and building on the achievements of others who built on the achievement of others, and so on, going back decades. So let me jump into what a quantum computer is and eventually answer the question, what the heck does this have to do with security? Okay? And there will be a test at the end. But, what's a quantum computer? Well, what's a classical computer? Because I think we often have a very rigid notion of what a classical computer is. We think it's one of these. But really a computer, the fundamental is what's inside one of these, which is just some chip that can somehow, you can store information, you can code information in it, you process it, and you get it out. And it used to be mechanical, electromechanical, vacuum tubes, right? Colossus was a computer. Doesn't look anything like this, but it was a computer. Under the hood, it was it was the same, implementing the same model, pioneered by Turing and Church and others. So it's a collection of bits, two-state systems, and again, it could be a vacuum tube, a transistor, right? That's just a matter of implementation. Okay. And so what's a quantum computer? Well, what's quantum physics? One of my high school mentors, Bruce White, and actually the Math 3 atrium is named after him. He used to say, mathematics is a language, right? And quantum mechanics is a mathematical language developed to express physical theories. So it's like going from a flat Earth model or language for talking about the surface of the Earth, right? Two-dimensional mathematics, Euclidean mathematics, which kind of works, but at some point it doesn't work anymore. And the problem isn't that we're not measuring things accurately enough and we're not drawing them well, is that we're using the wrong mathematical language to talk about the surface of the Earth. When you switch to spherical mathematics, everything works, because it's a much more accurate, it's a sufficiently powerful language to talk about what you need to talk about. So physics had a number of paradoxes, and really, really smart people tried very hard to resolve these paradoxes, and they couldn't. And it's not because they weren't good physicists, it's because they were using the wrong mathematical framework. So quantum mechanics is simply a language for talking about physics that doesn't require you to talk about an electron being here or there, right? But somehow being here and there at the same time, whatever that means. Now, I say in some meaningful way because that language can be misinterpreted. And so some of my colleagues don't like saying it's in two places at once, but they don't have a better, then they say, well, you have to learn what a Hilbert space is and talk about superpositions. I'm like, sure, that's a great way to explain to people what it is. So with the caveat, so yeah, I'm joking, I'm not gonna test your Hilbert space theory. There's other stuff on the test, but that won't be on the test. So, in some meaningful, obviously the reason we invented a new paradigm is because the old paradigm didn't work. So you can't fully explain it in the old paradigm. But in some meaningful way, we needed to talk about electrons being in several configurations at the same time. And it's not just electrons. Because it's a language, these rules apply to everybody, everything. Okay, so that's what quantum mechanics is. People say, oh, it's this thick, painful textbook. No. Those are theories people developed in this quantum mechanical framework, right? And then made deliberately painful for the students. But the foundation itself is really simple. And it applies whether you're down to the Planck scale, the tiny micro, beyond nanoscale of quantum gravity, or the macro scale of quantum cosmology, or this beautiful sweet spot in between the nano and micro scale where we encode bits today. And we can encode bits in quantum mechanical media. So these little loops up here, which I can't tell if there's a pointer. Yes, there is. This little loop here, it's actually pretty big, right? It's microns. Like you can see it, like this is not that big of a magnification. Like nanoscale precision, but you can have current going one way or the other. And it's just amazing you can actually get quantum mechanical effects in such a huge thing with thousands of electrons. But some physicists would disagree, say I'm oversimplifying. Well, of course I am, but roughly speaking, you can have, thousands of electrons going this way represent a 0, thousands of electrons going that way representing a 1, for example. But the technology is engineered so well that you can actually have them doing one or the other, at the same time. Like that just seems really hard. How can the rest of the universe not know, which way it's going? And then the Heisenberg uncertainty principle will kill you. Like once you learn if you're going one way or the other, you can't be going both at the same time anymore. You lose the quantum effects. But amazingly, they're able to isolate it. So it can be going one way or the other at the same time, and you don't know which way. Whether it's going this way plus the other way, this way minus the other way. It's just amazing that you could build these things. And this was the first prototypes of this as an actual quantum bit occurred about 20 years ago. Front page of Nature by our colleagues in Japan. So what's a quantum computer? Well, it's the same thing, except the bits could be quantum. So instead of these 128 bits representing one of the 2 to the 128 configurations, it can actually somehow embody all of them at the same time. Now, what's 2 to the 128? I remember Scott Vanstone once telling me, and to break this code would take like 2 to the 200 operations. And I was just, I was in my early 20s. I was like, well, is that a lot? Like, just doesn't sound like a big number. Like what if you just try harder, But now, that's just an insane, like a few hundred bits, like 2 to, 230, or like, that's just more than the amount of atoms in the known universe. So a few hundred of these things, and it's already an astronomical number. So what I'm trying to say is, so the physical reality says these 128 bits can somehow embody all 2 to the 128 configurations. That doesn't mean it's useful, right? Like, why should I care? And the first jolt to our, the emotional jolt for computer scientists was because we've had this principle for the last few decades that any device you could realistically build could be efficiently simulated by a regular computer. Okay, so like in the sense that a PC can simulate a Mac and a Mac can simulate a PC, there might be some overhead, like in practice that matters, but you're not going to have some exponential, you're not going to have the overhead, so to speak. The cost of simulating one with the other might be a factor of 100, or maybe simulating n steps might take n squared steps, but it's not going to be n versus 2 to the n, right? That was the thesis we've been working with for several decades. And then these physicists say, oh, well, that's wrong. It's like, well, okay, obviously you don't know what you're talking about, right? If A implies B and B is unpleasant, then not A, right? So obviously the physicists don't know what they're talking about, and we should just, of course, ignore them, which was my initial reaction. Then my supervisor said, well, maybe you should read about it and learn about it before you reject it. And then I started a quantum computing institute. So it's a bit ironic. I'm just glad I didn't stick with my guns, it's my initial intuition. So this is, this kind of jolted people and said, well, obviously there must be some reason you can't possibly build this. Because if you could, maybe it's good for something other than just simulating itself. Like cryptography, for instance, is based on these codes being hard to break on any machine, not just a Mac or a PC, right? And the Church-Turing thesis gave us the assurance that if it's hard on this sort of universal computer, it's going to be hard on any other one. But then this comes along and says, well, actually, if somebody could build a quantum computer, maybe it could break these codes. Sure, whatever. Like, their quantum computers are only good at simulating themselves, best case scenario, right? That's my gut feeling. Now, it turns out it's actually good for a lot more than that. And I'll elaborate a bit on what that means. But the technology that created an impetus to build and harness quantum mechanics in a host of information processing technologies. Along the way, we could potentially build sensors. Like one of the reasons we don't have a large quantum computer now is these devices are super sensitive. And so a lot of people said, well then, why don't we make good sensors out of these bits? Right? And there are companies founded now looking at building medical imaging technology. It's still early days, but maybe sensing landmines or other weak electromagnetic fields, doing better oil exploration and so on with other quantum technology. And I'll talk a little bit about quantum communication because this ultra-sensitivity, like what the Heisenberg uncertainty principle says is that if you extract this much information, you must disturb it this much, which is different from saying if you're clumsy, you're inevitably going to leave a trace, but you can get arbitrarily close to zero disruption if you're careful in a classical paradigm. But quantum mechanics says, no, there's actual fundamental trade-off. So you're going to actually probably disturb it even more, but there's like a guarantee that you're going to disturb it at least this much, and that's very useful. A new tool in the cryptography tool chest. So the applications we hear about, a lot of them are closely tied to simulating, what's something that is kind of like a quantum computer? Well, a molecule, right? If you're doing material design, if you're trying to design a new molecule or a new way to produce fertilizers that doesn't lead to as many nasty emissions, or design a new material, a higher temperature superconductor, we don't just go and guess a molecule and synthesize it because that's expensive. You can't do that 1 trillion times, even if it's $1 a shot, and it's a lot more than $1. But you simulate it in software to come up with a short list, and then you synthesize and test those. But it's hard to simulate a material if its quantum properties, or if the properties of it depend on quantum mechanics, you have this 2 to the 100, this exponential overhead. So we believe a quantum computer can help us simulate. It's still early days. I'm not aware of any sort of billion-dollar business plan. Here's the customer and this is how much we're going to pay them. Like, I want to get there, but we're not there yet. But we do have a host of promising applications. And a few years ago, we organized a quantum optimization workshop. Obviously, we're in the C&O department, and actually a couple of former faculty, Bill Pulley-Blank and Andy Kahn, were at this event in Toronto. This was the kind of thing we talked about there. What are the methods we use today in optimization that could be sped up by a quantum computer? And what would be the important industrial implications of them? It's actually pretty hard to find some. But here's one that one of my students came up with. He noticed the algorithms, so-called derivative-free optimization. The more dumb and brute force it is, the better we are at speeding it up. So the applications where there's clever methodologies already, it's harder to improve. But here, there's a part of it where they use just very simple method, and the potential is we could help design, for example, buildings to be better resilient to earthquakes. Again, still to be seen. So why don't we have a quantum computer yet? What is the path toward a quantum computer? Like back in '96, my supervisor, my examiners asked me, when are we going to have a quantum computer? And I did not want to answer that because I didn't know. But they insisted I guess. So I told them what I thought, and I said, definitely not for 20 years. And they actually thought I was being pessimistic. But I'd met a lot of the pioneers of the field at the time. It was still a small group. And they didn't even have the tool. They had some vague ideas for how they might build one. And they didn't have the tools to build the tools. Like, it was just, this is at least a 20-year project. And they were funded, but not that well funded. So I just didn't see it happening in 2 decades. And I was right, but I think we're a lot closer now. The reason our friends at Yale wrote this nice article outlining 7 non-trivial stages, right? So first you have to encode a bit somehow in a quantum system, and that's often engineering new systems that have never existed before. Sometimes it's just using an atom, right? But then the traps for trapping the atoms and controlling them is very new technology. There's a funny trade-off that I've noticed is the more natural the bit, the easier it is to get the bit to work, but the harder it is to integrate it into a computer with thousands of them. Right? And the more synthetic bits that are easy, you just design it and print out thousands of them on the chip. Sure, but then it's hard to get the bit itself to be stable. And then you get problems of, well, they're not all the same. Right? A cesium atom's a cesium atom. They're all the same. But these little loops, they're a little different by a few nanometers or a fraction of a nanometer. And that the fact that they're not perfectly identical does create an interesting software challenge for us. But anyway, we got to get multiple qubits. We have to be able to measure the bits, figure out what error occurred and correct it. Then this is the big milestone. We finally do error correction and get a logical bit that is actually much less noisy than the actual physical error rates. I'll explain in a minute more what that means. But this is the most important milestone. Then we'll enter a new era where we're scaling these robust logical quantum bits. And today, several platforms have achieved the first 3 stages. And I think once this 4th stage happens, there'll be a massive order of magnitude increase in effort and investment, which is already tens of billions of dollars. So I don't mean to suggest it's not significant at this point. So a logical bit, so this is just a cartoon of a physical bit. Could be any one of the approaches people are currently taking, whether it's one of those superconducting loops, an ion, or anything else. You get a collection of dozens or hundreds of them. So you imagine a chip with hundreds of little loops on it. These red lines and blue lines are just cartoons that mean, if you're near a red line here, it means apply a certain pulse, RF or microwave pulse, depending on the system, to the neighboring bits. So it's dozens, hundreds, thousands of pulses you're shining on these bits. And if you do all of this on hundreds, maybe thousands of physical bits, you've implemented what we call a controlled NOT. A controlled NOT is very much like an AND gate, right? It's actually simpler than an AND gate. If this bit is 0, flip this bit. That's all it is. It's a fundamental building block of computing. And to do that simple gate, you have to engineer hundreds, thousands of these things and apply hundreds and thousands of gates to them. This is the best known method we have today to robustly build one of these, and that's what we're trying to do. And if you notice, a few years ago, IBM demonstrated a 4x4 piece of such a thing, Delft 5x1, Google 9x1. And now they have 49, 50, 72, in some cases over 100 quantum bit, qubit pieces of this. It's still not enough to implement a fault-tolerant gate, but they're getting closer. But that's what we're monitoring now. I should say, along the way, people are saying, could we do something else with these bits? Can we still compute with them and not without doing full-fledged error correction? The answer is maybe. We'll see. But let's not just talk about our feelings. Let's demonstrate it, and I'll be happy. And if it doesn't work, I'll still applaud you for trying. But we don't know. It's looking more promising, I would say. So they might be able to get some quantum speed up for certain problems with earlier technology, which will be great. But most of my work is on scalable, fault-tolerant quantum computers where you can write any computer program and compile it to run on that hardware. You might want to reconfigure the hardware for that problem, but ultimately you can do anything a quantum computer can in principle do, which includes designing new drugs, optimizing the production of fertilizers, optimizing the layout of systems, and so on. And it's really moved from a physics, when I was summarizing the state of the art a decade ago, it looked like a physics experiment, right? And then in the last 5 years, it started looking like a chip, but it was still largely in a research lab in a university or maybe IBM research. But now there's a much, much bigger investment. They're looking like computers. They're working with teams, with engineering teams, and in organizations that can quickly attract the capital and scale and solve the engineering problems if needed. Many big names all around the world, mostly superconducting qubits that I alluded to earlier, but also some ion trap. So, atomic clocks, for example, they have a collection of cesium atoms, and the oscillation between 0 and 1 of the cesium atom is how we define a second today. And our friends at NIST realized they could leverage that atomic clock technology to build quantum computers. And that's one of the front-running approaches. China has recently entered the game. They've been in the communication game for many years, but recently, the government, then Alibaba, and then Baidu and Tencent, like billions of dollars. They're just ramping up, but very smart people who are already starting to do some very interesting work. So we're already in the tens of billions of dollars allocated for this. This perhaps jolted the United States to, people ask me, who's winning right now? Well, right now, I think the US is, but China's catching up very fast. So they've actually, amazingly, got a bipartisan bill passed and signed into law. It's not a lot of money. It's a lot of money for us, but compared to the tens of billions that China's putting in, I think it's a lot. It's $1 billion or so, but it's at least moving things in the right direction and helping coordinate and organize things better. So a litmus test for me about whether people are serious about building a quantum computer or really just is it an excuse to do exciting physics is, do you have a software stack? Because if you build a computer and don't have software for it, it's just a really expensive paperweight. And in the early days, they were pretty not dismissive, but it wasn't a priority, let's say. And to some extent for good reason. If you don't have the architecture, then how do you know what to write the code, how to develop compilers and so on? But that has changed. Most of the major vendors, at least industry vendors, building quantum computers also have some part of the software stack, from languages down to compilers and machine code. And our friends in Toronto are coaching, mentoring, they're incubating companies that will use quantum computers. So it's really the full stack is being worked on. And Canada actually has been one of the leaders in developing key parts of that software stack. Right, so a lot of my personal work in the last decade, in the first 20 to 10 years, for the last 20 years I've been working quantum algorithms. In the last 10 years I still work in quantum algorithms at one level below the stack as well and compiling them efficiently to run on realistic hardware. Because that's important, right? Do I need 1 million bits or 1,000 bits to solve this problem? That's years and years of engineering between the two. So just to give an example, a quick example of the kind of work I do and my team and others, there's an important gate called the Toffoli gate, named after a colleague of ours at Boston, Tom Toffoli. It's a 3-bit gate, which, if the first bits are ones, flip the third bit. Right? So that actually is a reversible implementation of an AND gate. Okay. It's hard to physically build a Toffoli, like a one-shot Toffoli gate. What we do is we break it up into things we do know how to build. Actually, the hard part is building it fault tolerantly. Okay. So we want to break the Toffoli gate into things I can actually do in the lab. And very importantly, these are, what these represent doesn't really, this is a controlled knot. H is a gate, a simple gate. T is another math gate, right? So maybe I should say, when you look at like flipping an atom, right, flipping a bit or applying one of these quantum gates to it, mathematically we model it as taking a vector and multiplying it by a matrix, right? So in the lab, it's, you shine a laser on something and affect some linear operation. When we analyze it as computer scientists and mathematicians, it's multiplying a vector by a matrix. So we take the desired matrix and we break it up into something that they actually know how to implement in the lab. So that's how we help. And this really, really important gate, which is basically the building block for most algorithms, breaks up into something like this. But it's actually worse than that. If you look at the actual, when remember I showed you that grid with the red and the blue lines, like a simple C0, like one of these things, I said is actually hundreds of bits with thousands of gates on them. This T gate is like 10 to 100 times uglier, even worse. So if you blow this up into the actual cost, this is almost entirely dominated by these T gates. It doesn't matter what they are, but it's a matrix that is really, really hard to implement fault tolerantly. And if you want to optimize the physical cost of implementing an important algorithm, you want to minimize how many of these T gates you do, and you want to do them as parallel as possible, because that reduces your time. You don't want to do them serially, because that could take forever. You want to parallelize them. And we use some very simple brute force methods, like smart brute force method called meet in the middle. It's a very basic technique in mathematics and computing. We came up with a better implementation of that, and then our friend at Dalhousie looked at what we came up with and said, hey, I can parallelize that really simply. And we're like, oh, you're right. Like, why didn't we see that? So then we said, you know what? We can generalize that. We see what you've done, and we generalized it to a much bigger class of things. And furthermore, we didn't want, like time memory trade-offs are great, but memory is also very expensive. And we said, what can you do with a fixed amount of memory? And my student wrote out, well, this is the optimization problem. And I said, well, that looks like a matroid. And he said, what's a matroid? I said, well, look it up. Because that's what I had to do. No, actually, I was very lucky. My supervisor, matroids, obviously, Bill Tutt was actually, I think the foremost figure in matroid theory for several decades in the 20th century. And my supervisor wrote the classic textbook for matroid theory in late to mid 20th century. So I knew what it was, right? And it was indeed a matroid. And turns out there was a polytime algorithm developed by Jack Edmonds here in the early 70s that solves that problem. So we had an efficient algorithm for optimizing the allocation of T gates, and it significantly improves the cost of running some quantum algorithms. So it's very serendipitous, right? I kind of doubt that Bill Tutt and Jack Edmonds and Dominic Welsh and Bill Cunningham, who was Jack's student, would have anticipated that, as they were just doing this very fascinating mathematics at the time. So I'll just cut to the chase with this one, but there's another, like I said, we want to do this physical thing. It's this weird matrix. We have to break it up into things we can actually do as approximately as we can, and there's a lot of deep mathematics underlying it. We developed a whole new paradigm for doing this, which first said, okay, what can we do exactly, right? And then how do we round off to something we can do exactly? So this is what I want to do. I can't do it exactly. And so we broke it up into 2 steps. First, let's understand what can be implemented exactly, and then find something that's as close as possible to what you want to do. But it's not rocket science, but there's a some things can be rounded off, some things can't be. So there's a lot of Diophantine approximation. So we talked to our number theory friends. But the point, the cool thing I want to tell you about is we wanted to rigorously show that you could, in polytime, round this thing off to something you could synthesize. And my student came up with this great idea. He said, well, what if I add 2 ancilla bits, initialize them to 0, and return them? Right? Just contribute it back. I'm just borrowing those 2 bits. I'm like, well, that's okay. It's better than nothing. It's a constant number of bits. And he said, well, the round off problem in that, because rounding off to something that has like Euclidean norm 1 is, I said, this is either going to be really easy or really hard. It turned out to be really hard, unfortunately. But if you add 2 bits, the round off question, so you can round sine plus cos to something over 2 to the n, but then it's not going to have norm 1. There's a tiny little deviation. And we needed to find small numbers a, b, c, d, such that a squared plus b squared plus c squared plus d squared equaled that deviation m. M is an integer. Okay, and I'm like, wait a minute, I've heard of this before. This is the Lagrange 4-square theorem. Completely, like who would have thought, so there's a theorem in math that says any integer can be written as a sum of 4 perfect squares in at least one way. You think, well, that's cool. Completely useless, but very cool. Right? And then Jeff Shallett in our computer science department and the famous cryptographer Michael Rabin in the 80s figured out an efficient way to do that. So we coded it up, and because this was, this is important for optimizing the compilation of quantum algorithms. Now, this result itself has been superseded by other number theory methods, but I thought this was really neat that, again, very deep mathematics, you never know what it could be used for. Fundamental undirected mathematics, targeted research, they're both very important and valuable and very complementary. And we developed all sorts of other tools for doing optimizations, including the application of Reed-Muller decoding. Reed-Muller decoding is useful in communication theory. Again, we just started saying, well, what does it mean to optimize this? And my student recognized this is actually a Reed-Muller code. So any improvement in Reed-Muller decoding, which again is a standard method for communication scientists, would give us better quantum compilers. Now, this is what my friend calls happy quantum. There is, with any new capability, there comes a responsibility to mitigate any risks it introduces. Now, sometimes we like things to be hard. And one of the pillars of our digital ecosystem, the security of it, is that factoring is hard. Right? Multiplying numbers is easy. Factoring numbers is hard, and that's what's called RSA cryptography. We use it all. HTTPS, that little s, relies on this, or elliptic curve crypto. So we want that to be hard, except quantum computers, that's just one of the weird things it happens to be really, really good at. And it's just a fluke that Peter Shor, actually he's a combinatorial, he did a lot of really important work in computational geometry. Brilliant colleague at AT&T Bell Labs at the time. Saw, there's paper, one of the seminal papers in quantum computing was, of course, rejected at the time. But he was one of the referees, and he said, I think I can adapt these methods and factor large numbers. Right? Now, fortunately, the devices didn't exist. It's kind of like what Ron and Scott and Ian did, where they figured out how to break something before it was deployed, right? So nobody died. Similarly, Peter figured this in '94 before anyone had a clue how to build a quantum computer. So there's plenty of time to procrastinate and not fix the problem. And it's a big problem, right? Because it underpins the our entire economy, basically. Depends on tools which use security protocols which use things like public key crypto or symmetric key cryptography. Quantum computers decimate the public key crypto side of that. It weakens symmetric key crypto. Easy to fix in theory, not so easy in practice. But with the most dangerous part is the public key cryptography. Now, people will often say, well, look, crypto's not the problem. Who cares? There's so many other threats to our cyber systems. Like, why? So what if this other one, gets a little worse? It's like, you're missing the point. I mean, most of these have nothing to do with mathematics, and this is how most hacks are occurring today. But if you order them from bad to worse, it's, these are, with just about anything, what you try to do is you reduce the chance that something bad happens. If you're responsible, you have some mechanism for detecting if something bad happens, and you have a protocol for remediating when something bad happens, right? You can apply this to just about anything, but that's sort of the framework we have in cybersecurity. With all of these things, there's clearly, if it didn't kill you, there's a way to remediate, right? User errors, well, we have that all the time. But you might have to rebuild, ransomware, there's a way to remediate. You pay it off, or you restore from a backup, or you shut your company down, but hopefully, but the point is, we know what happens, like Paul Kosher said this at RSA recently, we kind of know what happens when 1% of our systems go down at any one time. What we don't want to face, what we don't know what happens is they all go down at the same time with no remediation in place. And fundamentally vulnerable crypto, like what do you remediate with? Right? Heartbleed is sort of in the nasty part of this chain, right? Implementation error. And it was a buffer overflow, so it's not rocket science to fix that, but it still took many cases a year to get it through the full supply chain with all the proper quality assurance and testing. And that's fixing a buffer overflow. But with crypto, you can't just implement the same vulnerable algorithm. It'll still be vulnerable. So what has ironically become my most famous theorem, so how soon do we need to worry? Because Scott Vanstone would say, can I wait till I retire? Now, he was half joking, but other people weren't half joking. They were totally serious. Because some information has a shelf life. Well, it all has a shelf life, X years. And the most sensitive information, like trade secrets, can be many years. It takes time to migrate. Ask Ron and the others, how long did it take for ECC to go from an idea to a globally deployed product? Decades to do it properly. And then what is Z, the collapse time? How many years before quantum computers actually threaten these systems? And for the next Y years, we're stuck with these vulnerable tools because we haven't had a chance to deploy ones that will resist quantum attacks. We're supposed to provide X years of security, whether it's confidentiality or integrity. But if X plus Y is bigger than Z, then worry. You have a problem. You're already too late. Because the information, these last few encryptions, for example, won't be secure for X years. They'll be for sale on the dark web or used against you in some other way. Now, if Y is bigger than, so even IBM now and others are starting to repeat this message. I tried to make it as simple and graphic as I could so people would get it. And it is, this approach is, I think NIST calls it the Mosca theorem. Yeah. I don't tell people what the actual theorem is because it's really not a deep mathematics, but it's had some impact. Now, if Y is bigger than Z, systems will collapse. Right? And that's bad. Okay, we want to avoid that apocalyptic situation. But if we do avoid it, but we do it as a last-minute crisis management, there's going to be a lot of software. Like you saw Heartbleed happen because of a buffer overflow. You're going to have a lot of those. So we don't want to rush it. And the other risk, even before we have large-scale quantum computers, is people just lose confidence in the systems. When is this day going to happen? Again, I went from saying not for 20 years to, well, maybe in 20 years, like 1% chance to 10% to, now I say it's a 1 in 6 chance in under 10 years. Other people disagree, but we don't know is the correct answer. But that's sort of, anyway, I won't say the mathematician joke, but so that's, we don't know, but we can't afford to take a chance. So there are solutions. So what I'm alluding to is we have to deploy new cryptographic methods that resist quantum attacks. And many researchers at Waterloo are working on those. And another method, co-invented by a colleague of ours at Montreal, Gilles Brassard and Charlie Bennett at IBM, is quantum cryptography. So in addition to just trying to reestablish a status quo, the beauty of quantum mechanics is if you get this intrinsic eavesdropper detectability, and they leverage that into a way to get key agreement, the way to establish cryptographic keys so you can't mathematically cryptanalyze it. And these work well together, so we have a new set of tools with which to rebuild the foundations of our cybersecurity. The quantum cryptographies, invented by a Canadian American, developed with Europe, and then first, there's an approach to do it in free space by communicating to satellites. That'll help us get global distances. And that was first implemented by our friends in China, and Canada's aiming to be the second to enter this new era of quantum communication. Now, my take is, when I first heard of quantum cryptography, actually Scott Van Stone shows me this article, Scientific American. I'm like, whatever. This is science fiction. It was quite ironic. Then I met Gilles Brassard at a conference in '94. I was like, so I'd read his classical crypto papers, and I'm like, well, so what are you working on now? It was like quantum. I'm like, man, he's really gone off the deep end. It's really sad, Of course, ironically, then I co-authored a paper with him later in quantum computing. But my take when I eventually got it was, cryptography that can't be cryptanalyzed, that's a useful thing for protecting people and cyber systems and the economy against. It's not going to protect us from all threats, but that's a really valuable tool to have deployed so to actually help keep people safer. But what good is it if we don't use it, right? Sitting in research papers or prototypes in labs or just proof of concepts. So I've been spending a lot of the last 10 years figuring out the gaps to getting it into globally deployed solutions. And we have to do it in parallel. We can't wait till they're built and then hope somebody adopts it. I think we need to solve, it's a chicken and egg. Unless there's a business and use case, they're not going to build the networks and so on. So there's a lot of network flow optimization here. How do you turn point-to-point key agreement into a truly global network solution? There's a lot of combinatorics in there. So we've developed the algorithms, developed the software tools, made them available open source just a few weeks ago, and we're hoping that starts to spur more deployment. We've also made the classical algorithms available in open source, again, to facilitate testing and integration into solutions and really kind of get this show on the road, to bridge the deep mathematical ideas, which I love, into actual practical applications. Standardization work, we've also been really pushing, because one of the obstacles to having these tools deployed in practice is they need to be standardized. You can't have everybody having their favorite algorithm, because we all need to communicate with each other with a simple set of protocols we all agree on. So that's a very hard thing to achieve, but again, talking to my friends who made elliptic curve cryptography a global standard, we kind of knew what the template was like, so we've been prodding that along, both quantum cryptography standards, and we've been definitely supporting this effort. And they'll standardize something by, we think, 2022, 23. Sounds like a long way away, but we need to be ready to hit the ground running. And very importantly, we don't want to repeat, just like Ron and others found out that these Diffie-Hellman schemes that were being deployed were actually vulnerable. We don't want to deploy them and then find out there's an easy break for them. So myself and a number of my colleagues here and around the world have been working hard and studying these tools and making sure they can't be broken by a quantum or classical computer. There's many, many research challenges underpinning that. Waterloo has met much of the research, the background knowledge and talent and students to tackle those problems alongside others around the world. But there's certainly a long, road ahead here. But we're fortunate to be able to, at Waterloo, be building on the shoulders of giants. Like when I was at Oxford in the late 90s, I had the chance to stay there, basically. But I was, offered this great opportunity to try to build something in Canada. And Waterloo was the ideal place for what we were trying to do here. Not because we had, a quantum computing effort here already. There were the seeds of it, but because we had the great potential, the great talent pool, expertise in the combinatorics, the cryptography, and so on, to do something great. And I think we've come a long way. But it certainly didn't happen in a vacuum. We've also, the math is important, but one great thing our math program does is it requires our students to take a course in communication and leadership, which is an important part of taking the great things we do and having them have positive real-world impact. So one of the things I've done with others is articulate this cryptographic problem and challenge in business terms, in risk management terms. Because ultimately that's the language most of the decision makers, that's how they analyze it. There's a risk and they have a whole paradigm for doing it. So we tried to reformulate it in a way that they can plug it into their existing risk management paradigms. So, cutting across, so we have to, mathematics is a really critical, integral part of tackling many of society's challenges now, and we have to collaborate with the engineering sciences, the physical sciences, the human and social sciences, and we have a long, long history of doing that. So just to wrap up, on a positive note, because I opened, there's a great problem and threat here. This quantum threat, and it's the solution required to meet it, maybe is a blessing in disguise, right? Because it might seem like, well, that was an unfortunate thing, that quantum computers break the tools underpinning the security of our digital economy. But maybe not, maybe because it was far from perfect. There's many vulnerabilities just in what we're building on, there's a patchwork, right? It's normal because hindsight's 2020, so I'm not criticizing the people who got us here. There's many great tools, but then it's hard to get the business or political buy-in to fix something that isn't broken. Vulnerable is not enough. It has to be broken. It has to be on fire for people to then say, oh, maybe we should have fire trucks. But right? Until it actually happens once and somebody you actually care about suffers, it's really hard. But then the blessing in disguise is this quantum threat, it's actually fairly simple to articulate. The solution is hard but not insurmountable. It's forcing us to to rebuild the foundations of cryptography and thus of cybersecurity. Something we really realistically would never have done otherwise, right? So we have a choice. We can rebuild this flimsy, flammable foundation. Not flimsy. I don't want to beat up on it too hard, but it is very vulnerable. We can rebuild it through proper, proactively life cycle management and have a much stronger foundation that makes us not just resilient to quantum attacks, but more resilient to other attacks. So that's what we're trying to achieve. The alternative is we procrastinate and do crisis management, and we have an even more vulnerable foundation to our cyber systems and digital economy. Of course, we're very hopeful, and we're spending a lot of time doing the research and spreading the word, and we are, I believe, building a much stronger foundation to our digital economy and our society. So thanks so much for your time and attention. I think there's a few minutes left for questions, which I'm looking forward to.
Thank you, Mike. Indeed, there's time for questions.
All right. Thank you very much for the presentation. Again, another presentation with a lot of impact on human experience going forward in the future. Question I have for you is and bear with me with this because there is a level of abstraction required with these type of discussions. In the classical, the definition of computer, you can get in, I don't want to get into the details of that, but you could see it where math and science co-build on each other in different layers. And you start with the actual physical world, and then you do a little bit of math, and you try to control things, and then you change the physical world into something historically called a bit, on-off. As you build on that bit, you get into logical constructs called circuits, and then you take those circuits and you build logical constructs with registers and other combinations. The key of my question gets into when you start putting the registers together and you apply mathematical theory, computing theory in the form of something like the Church-Turing thesis, as it connects back into those constructs engineering. From what I'm understanding of quantum computing, I don't think we're at that level of abstraction. We're probably still working with math at building some of the circuits and some of the registers. Is there something that is equivalent? Can you confirm that I have an understanding, my understanding is somewhat accurate? And is there an equivalent at some point where we get into the need for architectures like the von Neumann architecture that applies Church-Turing mathematical thesis and computing thesis? Thank you.
Yeah. So with regards to the Church-Turing thesis, we don't violate the original Church-Turing thesis because we can actually simulate a quantum computer, but with exponential overhead. We do challenge a strong Church-Turing thesis, which talks about the efficiency with which you can do that. So we don't change what's effectively computable, we change what's efficiently computable. But you're kind of right, but maybe 5 years ago or 10 years ago, because 10, 20 years ago, we were still working at the low, trying to build a bit, right? We weren't worrying about, well, some people were, but they were largely ignored, to be honest, and maybe it was premature. But some of them actually knew what they were really way ahead. So I don't actually know how it's going to play out. And because I was part of a big project that funded 4 teams looking at different types of programming languages, quantum programming languages. One of them was very high level, like functional or like new age, approaches to programming, which builds on decades of experience. The others some of them were much more low level circuit description languages, which was more from the 70s. In fact, I met some people who wrote Watt4. So I asked them, I met with them and I said, we could probably use your advice more than the people doing the fancy modern compiler stuff. But ultimately, we want to tap into all that knowledge. And I don't know what if the first generation programming languages we'll use will be more like, the Q# stuff that Microsoft is. So Microsoft has built, a version of an F# type, system that is a little more abstract, and others who are working with more low-level circuit description languages. My personal work is agnostic. I encourage that because I know we need it, but any intermediate representation of the circuits, and we'll optimize it down to the machine code. So we're starting to get to we do have a model for the architecture. We do have it's still largely manual, but we're starting to automate more and more pieces of it with the compilation process. We can manually walk through programming language, intermediate representation, down to laser pulses. It's still growing, and we want to build that community of experts who understand all what you were talking about. Because initially we didn't have, it was still just the mathematicians. Not just, but I mean, we knew ultimately we would need to engage more and more people. And it's starting to grow. And now the industry teams have really smart people working on that full software stack. And there's a lot of the more fundamental work being developed in universities in Waterloo and across the world.
Is it on? Yes. So you're talking about standards, and I'm thinking about collaboration. So right now, it seems that you're drawing from disparate pieces of mathematics and science, and that's good because they're all in their own pocket. But as you're moving toward a solution, I'm curious to what extent there will be collaboration, which is necessary for standardization. So do you have a sense that there is collaboration? What I'm trying to say.
Yes. And that's so hard. Quantum mechanics is hard and math is hard, but getting the social engineering problems is even harder, I find. So the reason when I came here in CNO, asked to work on quantum computing so they could keep an eye on me, as Scott said, I wanted to sort of replicate what I'd helped my supervisor do at Oxford, which was a very multidisciplinary center. Because it was still far too, in the early days, it eventually starts to segment, but in the beginning it didn't. It was the same group of people building and programming everything. So we quickly expanded, went to science and engineering and so on. So IQC is all about sort of that breadth on the fundamental research side. But we also need collaboration across the different sectors, the policymakers, the government, many parts of the government, and industry. And that's happening more and more. So I started 7 years ago. I started with one of the international standards bodies called ETSI. One of my business colleagues introduced us to them. We told them the problem, and she was great. She's like, well, let's have a workshop. And we brought together a handful of believers from industry and government and standards. And it was actually a pretty successful workshop in southern France, in Sophia Antipolis, the ETSI headquarters. These are the people who did GSM and look after mobile communication standards. So they know standards. They didn't know much about quantum computing or anything, but so we started this, and then the next one was in Canada, and then we went to Korea, and Europe, and Canada again, and we're in China last year, and we're going to be in Seattle this year. And it's grown into this massive event with, again, people who would otherwise never meet are coming here. I work hard on the program. My main part of the program is to try to make sure people understand the breadth of the audience and try to speak to the different sectors. It's slowly working, but there's certainly a long way to go. So there's still many communities we haven't really fully tapped into that need to engage. But instead of just having a Babylon with, we're kind of growing from a nucleus and expanding it. I hope that answered your question. But
I also see security issues in terms of when you get to a solution, somebody's like, aha.
well, then we're in dialogue with the security folk too. I mean, the information security people are very engaged in this process. Well, my take is, let's take the threat side off the table. So, it's not a weapon of mass destruction when it happens. It's just, a cool high-performance computer, which of course will be export controlled and everything, but more of the same. And we can do it. It's in our control to get rid of the codes we know will be broken. Not get rid of them, just add the additional codes. I think you should still keep elliptic curve crypto because it's your best defense against classical attackers, and include one of these other codes on top of it to protect us against quantum attackers. Make the whole system more robust against all the known attacks, and then just take the threat side of quantum computing off the table.
Okay, maybe in the interest of making it to lunch on time, we can have one more question. And
thank you so much for this amazing lecture. I see your lecture in two parts when you talk about building the physical layers of the quantum computers and then coming to the algorithm and security part. So I was wondering, if the best quantum computer we have is of 100 qubits, so how do we actually implement the algorithms of which can be used in quantum computers and which can be used to attack security or save security? So I'm not able to connect those parts.
So I'm not sure I fully understood the question. You said 100 qubits? Or?
Yeah, if the best we have in physical, quantum computers, 100 qubits, so are we implementing those algorithms, quantum algorithms on those qubits? Or?
Right. So, you can do the algorithmic design. Most of the, even compiling the code, you don't need the actual computer there, right? So we can do a lot of it, almost all of it, for me, except for, running it, without actually having the device. So we have a model for it. We can do full resource estimation. We know how big of a hypothetical computer it would take. We know how long it would take. And what we're doing in the short term is we will do a 100-bit version of it as a proof of concept, just to validate the full tool stack, that we didn't forget something or that there isn't some silly glitch or gap. So we can do the 10, we can just simulate 25, 30 bits easily, but we can nowadays even try the algorithm on a 70, 50, well, that's easy. It's not quite that easy, but we're soon at the point where we can test it on a few dozens. It's still not likely to be useful, but we can sort of validate, validate the software in this small version. But otherwise, actually, there's a whole theory of verification of your code, which still needs to be developed. There's still so many challenges. And we're obviously borrowing all the methods people have developed for classical computing, but some of it doesn't work. You can't debug. You can't have a debugger where you just stop and look at because if you look at the state of the quantum computer, you'll collapse it. And so some of the standard debugging methods don't work. Some do. So there's still actually some really interesting. And these are the kinds of things you uncover when you try to do the proof of concept. Because, I mean, there's just something I'm doing right now where somebody thinks they can do something. I'm like, no, you can't. And they're like, well, here, run this algorithm and tell me if it works. But then if it doesn't work, he's going to say there's a bug in my code, right? And then, well, who's right? Right? And so I'm like, now I have to somehow prove that, no, my code's right. It's your stuff's wrong. So that we're encountering now because we're doing small proof of concept things.
Thank you.
Yeah.
Okay, so maybe let me conclude this question session here. And maybe have more questions offline. Let me thank Mike again for his engaging talk.
Thank you.